Alright, so here we have our Compact Logic L23E, and we have this wired up through a terminal block. So I have two Red Lion converters here, and the left one is set up for a voltage to handle 0 to 50 volts. So I'm wired into connector 9 that can handle either 50 or 100 volts. And then my common, you got an orange connected in the common there, which is the ground for that. So between there, it's going to be measuring the voltage, and then it's going to be outputting here the blue and white wires. Then it's going to be outputting a 4 to 20 milliamp signal, which I'm running into channel 0 of my analog card into the PLC. And then the ground wire is connected to the positive side of the other converter, which is going to be reading current. So this is our circuit here. So we have the first converter up here is measuring the voltage across our load resistor, and the second converter is reading the current, and we're using a shunt because the converter can only handle, it can't handle the total amount of current. It can only handle a small amount of current, so we're using a shunt. So I have a shunt in here, and if you've seen my other video, it turns out that my shunt, I didn't actually measure the shunt. I just kind of cut it and put it in, so it turns out my shunt is a little bit shorter than it should be, so my current is a little bit low. So I'm going to go through the scaling to correct that instead of changing the size of my shunt. It's better to have the shunt a little bit short with a little bit less resistance, so that you know that you don't put too much current through your converter. If too much current goes through the converter could be fried. So having a shorter shunt, which is what I did, I just I sort of measured it off, but not real accurate. I just made it a little bit short, and it's a little bit off. But so here is my shunt wired in to the positive side. So I'm using the orange. The orange is this intermediate connection here. So I have my power, the red, if we can see that way over here, I have the power, the positive voltage on this side of the resistor. Now, woo, I've had this thing running. It's running about it's running at 10 volts. Okay, so it's running 10 volts through this resistor, and boy, this thing's getting hot. Okay, this has been running for maybe 4 or 5 minutes now, and this resistor is very, very hot. So you don't want to keep this thing cranked all the way for a long time, because I can't keep my hand on this. This resistor is very, very, very warm. All right, but here's my power resistor. It's a 5 ohm resistor, but it can handle 225 watts. So right now I'm putting about 200 watts through it. I'm at 10 volts. It's 5 ohms, so that means 2 amps. So I'm putting about what did I say, the 10 volts times 2 amps. So I'm putting 20 watts through it, I guess, not 200 watts. The thing would really get hot if I was at 200 watts. But I've been putting 20 watts through this for several minutes now, and this thing is extremely warm. I can't imagine how hot this thing would be if I was putting 200 watts through it. Okay. But so this is a power resistor that is designed to handle that, but it will get very hot. All right. So here is my compute statement, and I'm scaling the voltage. Now remember that the configuration here is set up so that the input is bringing in 0 to 20 milliamps, okay, using engineering units, which actually means that they're microamps. So if we look at our tags, I have a tag called voltage underscore microamps, which is actually my input. So it's actually microamps, but it's the reading of my voltage. So it's the actual reading of my voltage. And then I have the current microamps, which is if it's reading into the analog card is microamps, but it's actually a current reading, which right now should be 2 amperes. All right, and so then I'm using a compute statement to compute that. Now the voltage, I've got some noise in the system, so it's bouncing around a little bit, but the voltage is at 10 volts. I showed you that the power supply is really holding at 10 volts, but this analog card is picking up a lot of stray noise. So so it's bouncing around a little bit, but you can see I've got it scaled, and it's basically reading about 10 volts, which is a pretty good scaling. But my current is a little bit low. I know that my power resistor is 5 ohms. And I know that it's pretty accurately 5 ohms, which means that my current should be at 2 amperes, but my current isn't quite at 2 amperes. It's a little bit low. So what I'm going to do is I'm going to rescale it. Okay, as I said, the problem is my shunt that I have connected there is a little bit shorter than my calculation. My calculation for the shunt was 1.5 inches, but I cut it to be more about 1 inch, which is why it's a little bit off there. But what I'm going to do, I say it's better to have your shunt a little bit lower resistance, so that you know that you're not going to burn out your meter. And we can just rescale this now. So what we're going to do is I'm going to come over here to my program tags. Now I'm reading my current. My current is reading here about 9,000. Looking at this, it's bouncing around here somewhere, but I'm going to say about 9,200 microamps. All right, so at 10 volts. So at 10 volts, I'm just going to write this down here. At 10 volts, the current is at 9,200 microamps. All right, so that's my first reading. And then I'm going to drop my voltage down. So I'm going to come over here, and I'm going to drop this down. I'm going to reduce my current. It's getting pretty hot anyhow, so I'm going to reduce my current down to where this is at about 2 volts. So I'm going to drop this down to about 2 volts. So before I burn my hand off, my hand is like real close to this resistor, and this thing is hot. Okay, so I'm at 2 volts. 2 divided by 5. All right, so that should be that should be about 0.4 amperes through that resistor. Okay, so at 0.4 at 2 volts, right? It should be about 0.4 amperes. Okay, and let's read the value here. All right, so that is reading. It's bouncing around some more here, but I'm going to say about 54. Okay, so the first one was 2 amperes. I wrote 2 volts, but at 92 microamps. And this value is about 0.4 amperes, and it's reading, I guess I'll just say an even 5,000 microamperes. All right, so we want to calculate our slope then. Our slope is going to be the large value, which is 2, minus the small value, 0.4, divided by the large value, 9200, minus the 5000. Okay, and oh, this was the wrong window there. So I'm going to calculate this. I'm going to use my Octave program I have set up here. All right, and so we have m is equal to 2.0 minus 0.4 divided by 9200, parentheses, 9200 minus 5000. And so we get our value now. Our slope value is 380. 000, so there's 1,000, so it's 0.381. So I just call it 0.381. So I'm going to come back over to my code here, go offline. I'm going to edit this. See, I had that scaling factor was 0.3125, but now I'm reading that it should be 0.381. So my current should be 0.381. And then I got to calculate my B. So I'll pop back over here. So my B then is going to be equal to the 2 minus M times the 9200. And so it should be minus 1.5. And I had 125 there. So now I'm going to download this change. I'm going to download the change. And as you can see here, hopefully you can read that okay, that the voltage is now reading 2 volts, bouncing around some, but effectively about 2 volts, and I'm getting about 0.4 amperes. So I'm going to crank it back up. I'm going to crank it back up to the 10 volts. And I should be about 2 ampere. So we're back up to about 2 volts. And I didn't put a meter on that, so I'm not quite sure how accurate that voltage is. But we can see we're back up to 10 volts, and we're at 2 amperes. So even though my shunt was a little bit short, I was able to scale it, so now that my current is reading much more accurately. So it should be, right now I'm at 10 volts, and my current is reading 2 amperes. So that's a much more accurate reading there. So, so this is my voltage. I'm calculating my voltage. Now I have a standard seal-in circuit here. Now the seal-in circuit is configured with both a physical start-stop and a virtual start and stop, so that I can connect this to an HMI. Okay. So if I press my start button, it begins running. And so what I've got here is I've got a bit which I call delta T done. So this is my delta T done bit, and I'm just setting this on so that I can get a, you probably hear that clicking there. Okay. So you can see that that delta T bit I'm just using to turn on the amber light. That just kind of tells me that my timer is working and just gives me an indication about how fast my timer is working. So what we're doing here is we're doing integration, and so we need to calculate the energy. And so the first thing that I have here after that amber light bit, turning that on, is I have my stop button. So if I press my stop button, it resets my energy, my average power, and my P1 to 0. And it also resets the watt hour, and it calculates the new voltage. Okay, so, or the new power P2. So it's calculating the power P2 in there. And so it resets my values. Then I have a master timer. So the master timer is just going to run for 5 minutes here, and then it's just going to shut off the system. Okay, so to do that, actually, I see I left that out of here. Inside of my sealant circuit up here at the top, I need one more bit here, which is going to be the master timer dot done bit, and I want that if it's not done. Okay. So if the master timer is not done, we want this to run, and then when it does reach done, we would need it to stop. All right, so I'm going to download this change. And so it starts, I start the system, and the system is running, and when the master timer is done, it will actually shut off here. And so you can see it, the master timer counting here, and when it's done, it'll give me my total energy. Okay. So the delta T is how often I'm calculating the time. So right now, every half a second, I'm calculating my time. So there you can see my, actually I had my master timer set for 30 seconds there. So it wasn't running for very long. But so let's just go down through this code and look at this code. So I have my delta T. This is calculating every time the delta T is done, it's going to calculate how much energy was used within the previous time the delta T was done. So I'm calculating new energy. So here's my delta T done tag. And I'm setting that bit, which is going to turn on that amber light. And then I'm setting segment A, B, and C. Now these calculations here I'm doing to kind of spread out the calculations. But I'm tying them into my delta T. So if I change delta T, I want to be able to change delta T on the fly. And so I have to calculate these depending on the change in my delta T. And then I'm calculating my energy. So I'm calculating the energy here. That the energy is equal to the previous energy plus the average power times the time step delta T. And then I'm calculating watt hours. So this is energy per hour. So this is energy per second here. This energy is energy per second, because remember, power is per second, a second or an instantaneous value every second. This was my power. Power average is my power. So this is energy per second, or energy for every, not per second, but energy every second. And so then I'm going to divide that by 3600 seconds to get a watt-hour value. All right. So watt-hour energy, we divide the second energy second divided by 3,600 seconds to make it an hour. And so you can see here in my 30 seconds that my master timer ran, I used 156 watt hours. All right, and so the then what we're doing here is at segment A. At segment A, I'm doing two things. The first thing is I'm going to move my calculation of power 2 into power 1. So there's no need in calculating the power twice. All you do is shift it. So I'm shifting power 2 into power 1. And then I'm also unlatching the light, so I'm shutting that light off. Then at segment B, when segment B occurs, I'm going to calculate my new power 2, which is, of course, power is just voltage times current. So I'm calculating my new power. Okay. I just realized I have one other miscalculation here. When I calculated energy, I'm using delta T pre, but the problem is that delta T pre is in milliseconds. The pre is in milliseconds, so I actually have to divide this by 1,000 to get it in seconds. Okay, so that's why my energy calculation was so large. I remember seeing that number and was like, for 30 seconds I did not use that much power. Okay, so you have to when you calculate your power, it seems like this is when you calculate your energy, delta T, remember delta T is in milliseconds, so we want to make it seconds, so I actually have to, this pre-value was 500 milliseconds. I need to divide it to make it seconds, and so that's why I'm dividing by 1,000 here. Okay, so let me just go ahead and start my calculation again. So here's the calculation. It's going to run for 30 seconds, and you see that the watt hour is adding up much smaller because I'm dividing by 1,000 here. So after 30 seconds, we'll have our watt hour. Okay, so but we're moving power 2 to power 1, then we're computing the new power 2, then we're computing the average power. And then that was my 30 seconds. So after 30 seconds, you can see that I used 0.16 watt hours. Okay, so that's how much energy that I used in there. All right, so I move power 2 to power 1. You have to make sure you do that in the correct order. You have to move it, then calculate the new power, then calculate the average power. Then the energy, when the timer is done, we calculate the new energy, which is the old energy plus the average power times the time, which is in seconds. So it's the pre-delta T times seconds. So that is our code to integrate to determine how much energy we are using. This is, the integration is right here. We're taking the energy plus the energy since the timer last finished. Okay, so that energy plus the energy every time the timer is done, we're calculating a new energy here, which is power average times the delta T.